So today we're starting with 4.3. We're going to look at two specific types of chemical reactions that occur. So the first one that we're going to learn about is called synthesis reactions, and the second one is called decomposition. So these are just basically two types of chemical reactions that occur, and we can represent them and see whether an equation is a synthesis reaction or a decomposition by just looking at the chemical equation that's in front of us, okay? And we're going to do a small activity before we finish today where we look at some chemical equations and we can identify, okay, that one's a synthesis, that one's a decomposition. Okay, so before we go into that though, we need to understand why we have different types of chemical reactions, okay? First of all, we have different types of chemical reactions and we give them different names because it becomes easier to classify them, because it becomes easier for us to predict what will happen or what kind of products we can get. For example, in a synthesis reaction, you've got two or more smaller chemical substances or products combining to form a bigger product, okay? And so we can obviously, make assumptions or make predictions on what the products will be as a result of that. In decomposition, a bigger compound breaks down into its smaller elements or smaller constituent substances. So we know that when we see a decomposition reaction happening, we know that we are going to see the different components or different substances or compounds that the bigger compound is made up of. Okay, combustion reactions are basically chemical reactions that lead to the production of carbon dioxide and water, okay, such as when we burn fuel, for example. And hydrolysis is basically chemical reactions that involve water. We're mainly today, however, just focusing on synthesis, which is also combustion is actually a type of synthesis reaction, as we'll see in the video as well, and decomposition are the main ones we're looking at today. Okay, so that's why we have the different names for the different types of chemical reactions, because it becomes easier for us to classify those chemical reactions and to make kind of predictions about what substances or what products will be formed as a result of that chemical reaction there. Okay, and we know that we've talked about in chapter 3 that elements in the same group have similar properties. Okay, for example, they have similar characteristics, similar reactivity, etc. So basically, when we look at chemical reactions, when we've got two synthesis reactions, we can see that the predictions of what products will be made might be similar there as well, okay, depending on which compound you're dealing with. So those are the types of chemical reactions. So the first one we're going to look at today is synthesis reaction, okay? So what I want you guys to do is and I'm going to test your knowledge here of vocabulary. Can anyone tell me what the word synthesis means in the chat box? Or if you want, you can just maybe look up the word synthesis and give me one word that describes what synthesis means. In the general, like just the word, okay, not the chemistry context, just the word as an English word. What does that actually mean? Excellent, combination, yeah. So basically, when I ask you to synthesize something, okay, and a lot of the time, especially in your VCE subjects, synthesizing is actually a really important skill. Synthesizing is being able to take many different bits of information and basically put it together to combine it, okay? For this reason, our synthesis reactions are also called combination reactions. In fact, it'll be easier for me to type, so just give me 1 second. Okay, so synthesis reactions are also sometimes called combination reactions because they involve two or more smaller elements basically combining together or kind of adding together to make a bigger substance or a bigger compound. And so that's why the formula that represents a basic synthesis reaction is A plus B. There's always a plus in between to show an addition or a combination that's taking place. A plus B gives us AB. So you can see here, those two elements that were separate in the beginning have now combined. They have now what we say as synthesized, okay? Synthesizing information, synthesizing elements means that those elements or those things are combining together, okay? Two small elements or two small substances combine together. And these are simple because they're by themselves, okay? They're simple substances combining or adding together to give us a bigger compound, okay? The most common example, which we've gone through quite a few times, is sodium, okay? Sodium, so Na plus chlorine, which is Cl, gives us the bigger compound, which is NaCl, which is sodium chloride, which is our ionic compound, which is a table salt, okay? That is basically the most simple example of a synthesis reaction. Okay, and we've got many others. We've got like potassium plus chloride, we've got potassium plus fluorine. All of those things combining together as single elements or atoms, they combine together to form a bigger compound, okay? So you'll always see, and the clue to look out for when we give you a bunch of equations and ask you, okay, which one is synthesis, which one is decomposition, look for the plus sign, okay? To the left of our arrow, these are what we call as our reactants. Remember from 4.1? So these are our reactants. In between the reactants, to the left-hand side of the arrow, there should be a plus sign that separates them. Okay, if that's there, you automatically know that this is a synthesis reaction. Okay, that's the formula. This is the same formula, just a little more colorful, I guess. That's about it. Okay, another really common example of a synthesis reaction is the reaction that leads to the product of carbon dioxide, okay? That's carbon plus oxygen gas that leads to carbon dioxide. And remember when we were doing our prefixes, what did we say di stands for? Which number? If anyone remembers, the di prefix. What does di stand for? 2, excellent, good work. So 2, okay? And that's why the symbol for carbon plus oxygen gas is CO2. Okay, because dioxide is basically the oxygen gas, and there are 2 atoms of that because of that prefix there. Okay, so again, that's another example of a synthesis reaction. It's not really that complicated, guys. It's just a matter of knowing. Synthesis is when you're synthesizing or combining elements from their simple form and they're adding together to make something more complex or something more substantial there. Okay, just let a few more people in. Okay, and then basically, if we go to the next slide, we're looking at just some questions about this. So what I want you guys to do now is to, and we actually did this last time when we were balancing equations for sodium chloride, I want you guys to answer the following questions on this page. So the reactants, which are obviously going to be to the left-hand side of your arrow, are sodium and chlorine. So you just have to write the symbols for them there, the chemical symbols, and the product will be sodium chloride. Then I want you to write the worded equation. So in words, no chemical symbols here, just English words, okay? And then I want you to write the equation using the chemical formula. So this is where our chemical symbols, NaCl, all that stuff will come up, okay? This is where you're writing the equation using the arrow, separating the reactants and products. So I'm gonna give you guys, this is a pretty easy question, so I'm not gonna give you guys too long, probably around maybe, let's say 3 minutes. Okay, 3 minutes to try your best and answer the questions on the slide. You can just write them in your exercise book or on a piece of paper, and then we'll discuss the answers. So 3 minutes on the clock, and your time starts now. Okay, so when we're looking at this, we're basically looking at the reactants. Remember, the reactants are to the left of the arrow. So if these are your products to the right of the arrow, your reactants are always to the left, okay? When we're writing the chemical formula for sodium and chlorine, sodium exists as a monoatomic molecule, which means it only has 1 atom, but chlorine actually exists as gas, as a gas molecule, which is a diatomic molecule. So Cl should actually be written like this, Cl2, okay? Not just Cl. Okay, all of those diatomic molecules, remember we used a memory tip for that. I think it was have no fear of ice cold beer. So hydrogen, fluorine, chloride, chlorine, iodine, all of those exist as diatomic molecules. So even for fluorine, if I was to write fluorine as a reactant, I would write F2, okay, not just F. This is how it exists in the chemical equation. Okay, anyways, we're not talking about fluorine now. So we would write Cl2, not Cl, okay? So this is the correct way to write it. So the products that will form is sodium chloride. Now we know the symbol for sodium chloride, so we can just write it down there. It's just sodium chloride. But how do we write this out, basically? We need to remember that when we write this out, why does it look like this and why doesn't it look like this? Can anyone tell me? I know this is very simple related to what we did, but I just want to make sure you guys are understanding. Why do we write sodium chloride's formula like this for the ionic compound And why don't we just write it like this, like how it looks like? We don't write the subscripts. Not necessarily. It's something to do with the swapping. Remember, we used to do this crisscross thing. What was that about? Can anyone remember? Okay, remember guys, when we used to do the crisscross thing, we said if Na has a plus charge and Cl has a minus charge, when we write the chemical equations, we do the crisscross and the numbers attached to the charges swap. So basically, Na will become Na1, Cl1, but we don't write the ones, yeah? So that's why the formula is this and not this. Okay, that's the basic, that's the reason. Write the worded equation. So now with the worded equation, all you're doing is you're writing it in words, okay? So you're gonna write sodium plus chlorine. Okay, here you're not writing chloride because we're just looking at it as an atom now. Okay, so sodium plus chlorine equals to sodium chloride. That's the, sorry, not equals to. I need to put my, let me see if I have an arrow symbol there. Yes, I do. Okay, that's not the arrow I wanted. Hold on. You know what, let's just do that again. Sodium plus chlorine equals to, sorry, not equals to, I'll just make an arrow like this, okay? Sodium chloride. Okay, so that's the worded equation. Worded equations are really easy. If we ever ask you a worded equation, it won't be worth much marks, but it's good to know how to write one, okay? And then write the equation using chemical formula. So this is where you actually bring in your knowledge of the chemical formula and you just basically write it down. So what we would do is and remember, whenever you're writing a chemical formula, the final answer that you give in a test or in a SAC situation or exam situation needs to be a balanced equation. Okay, and you'll notice that if we just write whatever was above here, just like this, like Na plus Cl2 gives us NaCl, that's not balanced. Okay, this is not a balanced equation. It's not balanced because we've got one sodium here and one sodium here, which is fine, but we've got 2 chlorine on this side and then only 1 on this side. So remember guys, what we used to do to balance it out, we used to put a coefficient. Okay, we put a big number in front of the compound that needs to be balanced, or in front of the element or atom that needs to be balanced there. Okay, so what we would do here, for example, if we've got 2 chlorine on this side, we need to make sure there's 2 on this side. So chlorine is attached to sodium, but that doesn't mean I can just put a 2 there. It's got to be right at the front of the compound, yeah? So if I put a 2 here, chlorine is now balanced. We've got 2 chlorine on this side, 2 on this side, but now sodium becomes unbalanced because now you've got 2 sodium on this side, but only 1 on this side. So that problem is solved pretty easily. Just put another 2 in front of this side. Okay, now this is our final formula. This is what you would write to get full marks. If you don't do the full balancing, you'd probably only get maybe half a mark or 1 mark. You wouldn't get the full mark. So just remember this when you're writing equations for the test as well. Okay, is there anything on this slide that doesn't make sense? Do you guys understand the difference between like a worded equation and then a chemical equation? Like if we were to give you this question in the SAC, would you, in the test, you should be able to differentiate between the two, okay? So that's the main idea there. So if something doesn't make sense, just please let me know in the chat box and I can explain it again. Okay, if not, then I guess we'll just keep moving. Okay. All right. Okay, what I've done is I've actually already answered these questions on the previous slide just now, but I haven't talked about the states. When you're writing a chemical equation, usually in the question we'll say, write a full balanced chemical equation with states. Okay, so if you ever see a question like this, write a full balanced chemical equation with states. Okay, sometimes we don't write with states, but usually we'll mention this. If we say with states, that means you've got to indicate the specific state of matter that the element or that the compound exists in. Okay, so whether it's solid, whether it's liquid, whether it's gas, okay, whether it's an aqueous solution. We'll learn more about aqueous solutions in 4.5 when we do precipitation reactions as well. Okay, so basically, if something is a solid, if we look at table salt or sodium chloride, we know that that's going to be in solid form. Okay, when we were learning about ionic compounds, we learned that a lot of our ionic compounds exist in a crystalline form. They form crystals, okay, and crystals are solid. Okay, similarly, if I have H2O happening in my chemical equation, water exists as a liquid, so it'll always be L. Okay, most of our metals exist as solids. So for example, sodium will exist as a solid. Okay, so that's the basic idea there. Okay, carbon dioxide will exist as a gas. So it's just a matter of putting the brackets underneath the element as you write it down. You're putting down the brackets, okay, as to what state of matter. Is it a solid? Is it a liquid? Is it a gas? Is it an aqueous solution? So that's what these little letters stand for, okay? And if we ask you for a question like this and we say which states and you don't mention the states, you will lose marks for that, okay? And that was probably some of the reason why a lot of students last semester lost marks, because they didn't put the states when they were asked to put the states there. Okay, so that's the basic idea. Any questions, guys, about about any of this so far? Look, I'm assuming you guys are okay because no one's asking me anything. Okay, so that's what I'm thinking. Okay, if you have any questions, you just need to let me know. Okay. Okay, and this is our, as we saw in the previous slide, this is our chemical reaction answer, okay, or explanation there. So you can see here, for example, sodium, as I said before, it's a metal, it exists as a solid. So that's why it's got the S symbol. Sodium chloride is table salt, which is in crystal form. Okay, if you go to your cupboard, take out some table salt, it's solid, okay, that's the form it takes. So that's why I got a little small S there. And then obviously with chlorine, we said before that chlorine doesn't exist as a monoatomic molecule like sodium does. It exists as a diatomic molecule, and that too, it exists as a chlorine gas molecule. So that's why we put the G next to the chlorine there, okay? So that's the basic chemical equation, okay, or the synthesis chemical reaction for sodium chloride. Okay, so we'll keep moving on. So now we're looking at just another example of a synthesis reaction. Okay, this one is the chemical equation of ammonia. So I've already put it on the slide for you. All I really want you guys to do now is I want you to balance this equation for me. So let's see how much we remember from balancing equations. I want you to balance this equation for me using those steps that we talked about last time. Remember the step-by-steps where we make sure there's an equal number of atoms on each side. So I want you guys to do that now, and I'll give you about, let's say 2 minutes to give this a go. Okay, so your 2 minutes starts now. Okay, so hopefully that makes a bit of sense. All we did was we just put the coefficients in order to balance it out. And guys, the main thing I want you to get from this is that this is an example of a synthesis reaction. Okay, these are not the only ones you're going to learn or going to see throughout this semester, but just to give you an idea of what a synthesis reaction looks like. Here you can see that the nitrogen and the hydrogen gas are combining or adding together to form a bigger compound, which is actually called ammonia. Okay, and ammonia is what we find in a lot of your bleach, okay, like White King, if your mum has the bleach in the laundry cupboard or whatever, those all contain ammonia, okay? Alrighty, so hopefully that makes a bit of sense. So now we're going to move on to our next type of reaction, which is decomposition. So I want you to think about everything you know about synthesis, about combining, about adding, and just reverse it, okay? It's just the opposite. Decomposition is literally the opposite of a synthesis reaction. It's when we take a compound that's already been combined and then we reverse that process. So we decompose. What does decompose mean? Can anyone tell me? Just what does the word decompose mean when you think about it as a word or as a definition? It means to break
apart.
Yeah, to break apart or to break down. Excellent. Okay, so to break apart or to break down. Okay, if we think about, you know, like plastic. Okay, when someone throws plastic in the ocean, we say it takes millions of years to decompose. Decompose means to break down. So when we're talking about decomposition, decomposition is just the noun form of decompose. Okay, decomposition means for a bigger compound to break down into its smaller constituent or smaller elements or substances there. Okay, so a bigger compound breaking down into a simpler compound or into the smaller compounds or substances that it's made up of, okay, to the elements that make it up. Okay, now decomposition reactions, in order to break down, because if we've already combined and there's already a compound that's formed and it took a lot of energy to get there, to get to this compound, okay, so in order for that to now break down again, there's a lot of energy that's required, and this energy is often required in the form of either heat or electricity. Okay, what this means is that usually by heating up a substance to a specific temperature, sometimes we can cause that compound to decompose into its elements, okay? This happens through a process called electrolysis, which we're not going to go through in too much depth, but it's just an example of how a bigger compound, like AB in this example, can be decomposed into its smaller elements that make it up, okay? So basically that is what decomposition is. Okay, if we think about the decomposition of water, water's symbol is H2O. That's the compound. And then obviously that can break down into its two constituent elements there. Okay, so it's important for us to be able to remember that. So we can obviously break that down into H2 and oxygen. Okay, so basically that's what gives us that kind of decomposition reaction there. Okay, so decomposition, guys, is the complete opposite of synthesis reaction, okay, or a combination reaction. Okay, so when we're writing the chemical equation for the decomposition of water, you're literally just, and if we think about the equation for water, okay, we've got H plus and then when you've got O2 minus, okay, when they combine and we do the little crisscross, that 2 number goes to hydrogen, so we've got H2 and that plus 1 goes to oxygen. We don't write the plus, we just take that as a 1. So H2O1 equals to H2O. And H2O is made up of oxygen, O2, which exists as a diatomic molecule, and H2, which exists as a diatomic molecule as well. Okay, so usually when we heat up water through electrolysis, through heating it up to a specific temperature, we can actually, we can say separate or lead to the breakdown of hydrogen as an individual element and oxygen as an individual element there. Okay, that's what decomposition reactions are. Okay, we've got some more here as well. So we've got, with alumina. Alumina is basically aluminium oxide, and there was a question about this in your recent test as well, if you remember. Okay, aluminium oxide, basically if we run an electrical current, okay, we said we can separate or decompose compounds through either heat or electricity. So if we were to run an electrical current through aluminium oxide, we would actually get the individual two atoms of aluminium as well as 3 atoms of oxide, that compose or that make up aluminium oxide. Similar thing for calcium oxide. Okay, if we were to if we were to run an electrical current through that, we would be able to get the individual elements of calcium and oxide. Okay, so that's the basic idea there. Okay, and calcium oxide is literally just a product that's caused by the decomposition of calcium carbonate. So calcium carbonate decomposes and it leads to the byproduct of calcium oxide there. Okay, so we'll look at these equations probably next class before we start, just as an activity. And because I feel like some of you still don't have your head around balancing equations, even though you're not really telling me outright. I can kind of see that because only a few people are always answering the balancing equation questions. So what I'm going to get you guys to do for homework is do a few more balancing equations questions. And then on Friday, before we start the new spread, we will look at the 2 answers for this one. Okay. And I'm also kind of aware of time. Okay. So when we're talking about the summary, so we've got synthesis and decomposition. So synthesis, again, is the building up of compounds. Okay, so we've got, for example, A plus B. Okay, this is the formula, gives us AB. Okay, that's for synthesis. It's the opposite case for decomposition. For decomposition, it's AB separates into A plus B. So it's kind of the opposite, okay, if we think about it. Okay, so using this knowledge now and having this information in your head, we're going to do just a few questions, the typical test questions that we give you guys in the test and exam, where we give you a bunch of equations and we ask you to identify or to classify whether that equation is an example of a synthesis reaction or whether it's an example of a decomposition reaction. So I'm going to give you a few minutes, maybe like, it's not too hard, maybe 2 minutes. I'll give you guys 2 minutes to write down in the chat box which the order of the following, in order, what the following equations are. Are they synthesis or are they decomposition? So we're just doing some classification here. I'll avoid putting an arrow. Okay, so I've got my pen ready. Who can tell me in the chat box? Calcium carbonate breaks down into calcium oxide, which we just mentioned before, and carbon dioxide. What type of reaction is this? Chemical reaction is this? Is it synthesis or is it decomposition? So in the chat box, you can either write D or S. Excellent, it's D, awesome. Okay, so this is a decomposition reaction. We can see that calcium carbonate is clearly breaking down or decomposing into its smaller substances there, okay, which are calcium oxide and carbon dioxide. Okay, next one. So P4 plus 3O2, what type of reaction is that? Is that synthesis or is that reaction? So in the chat box, you can either write S for synthesis or D for composition. Excellent. Yeah, it's synthesis. Okay, we can see a clear addition there. Okay, there's a clear combination of smaller substances to form a bigger compound. Okay, so this will be synthesis, or otherwise known as a combination reaction. Okay, what about the third one? So we've got some addition there, so that should give you a clue. Excellent, synthesis again. Okay, what about the next one? So O3 breaks down into O plus O2. What do we think that one is? Yeah, decomposition, because we can see a bigger oxygen molecule there breaking down into the smaller oxygen molecules that it's made up of. So this will also be decomposition. Okay, next one. So nitrous oxide breaks down into 2 oxygen atoms plus nitrogen gas. What would we say for that? So we've got 2 nitrous oxide breaking down into 2 oxygen and 1 nitrogen gas. Would that be decomposition or synthesis? Yeah, decomposition, excellent. Okay, so remember guys that in order for it to be synthesis, we need to remember that whatever's on the right-hand side of the arrow, it does matter where the elements lie in terms of where they lie on which side of the arrow. Remember in 4.1, we said whatever's on the left-hand side are our reactants, whatever's on our right-hand side are our products, okay? So it does matter in terms of where they lie. So this would be decomposition as well, okay? So the plus sign for our synthesis always has to be on the left-hand side in order for that to be a synthesis reaction, okay? The elements or substances need to be adding from the left-hand side to give us the products on the right-hand side. So just don't get confused. Sometimes when you see the plus sign, you might think that's synthesis, but it does matter which side of the arrow that those elements lie on. Okay, the last one. What do we think the last one is? So we've got ammonium plus hydrogen sulfate or sulfuric acid. What is the last one? And it's giving us a new product there of ammonium sulfate. So do we think the last one is synthesis or do we think it's decomposition? Yeah, synthesis, excellent. Awesome, guys. So it looks like some of you have a good understanding of the difference between decomposition and synthesis. Now, look, if we were to give you this question in a test or exam, I'm telling you now, this is one of the easiest questions that you can get. And it's a question, it's an easy question because you don't have to do any chemical equation writing. It's just a matter of classification, literally identifying. Okay, and like I said, as long as you can see where the plus sign is and whether the elements are combining to form a bigger substance or a bigger substance is breaking down into smaller substances, you can easily determine which one is synthesis and which one is decomposition. Okay. Also, one more thing to add is a lot of our combustion reactions, we haven't covered combustion in depth yet, but a lot of our combustion reactions that we'll look at later in chapter 4 are also examples of synthesis reactions. Okay. So that's also important for us to remember there. Okay, so that's literally it for today, I think. Yeah, that's it for today. Are there any questions about any of the content we covered today? Okay, let me just first stop the recording.